chemistry is the study of matter. We also know that everything around us is matter. We also know that the smallest unit of matter, if you take any one thing in front of you, the pencil, the air, you can break it down, break it down, break it down, and the smallest unit of that matter is atoms. The atom is not anything we can see. We have the molecular views of atoms and elements, molecules, and compounds. Since matter is made out of atoms, since we're made out of atoms, what exactly is the atom made out of? What the atom is made out of is smaller particles called subatomic particles. And those are smaller than the atom. They're inside the atom. And there are three main subatomic particles: protons, neutrons, and electrons. How are these particles arranged inside of the atom? You can't see inside of the atom. So this is all a model called the Bohr model. It's one way to picture the subatomic particles arrangement inside of an atom. So in the center circle, there's a nucleus. And this nucleus, this center circle, has the symbols P+, which stands for the protons. Those are the positively charged particles. That's why the plus sign. And neutrons. Those are the no charge. So that's a 0 with the N. Protons and neutrons have mass. So it's a very, 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 very small mass, but it's all the mass of the atom, essentially. That mass of the atom is all clustered. It's all centered in there in the nucleus. The nucleus of atom is kind of like the nucleus of a cell. It's in the center. Nucleus doesn't take up very much space, even though on this image, this seems to take up a lot of the space. Relatively, we already looked at the space of the nucleus is a very, very, very small volume compared to the rest of the space that an atom takes up. Now, what's in the rest of the space of the atom? Well, that's the space where the electrons can reside. So the electrons are the third subatomic particle, and those electrons have negative charge. So the symbol for the electron is E-. Electrons have negligible mass. They basically don't weigh anything compared to the protons and neutrons that have all the mass. But electrons do take up a lot of space. So there's kind of an opposite there. The protons and neutrons don't take up very much space, but they have mass compared to the electrons, which take up a lot of space inside of the atom. And it's not because they're large, it's because they're moving around. So electrons are taking up a lot of space and they have access to a lot of space. They're moving around in this space that is outside of the nucleus, but still inside of the boundaries of the atom. In this model, this is called the Bohr model, it has the electrons located in what are called energy levels around the nucleus. So if the nucleus is the center circle, the energy levels are the concentric circles that are around the nucleus, that here can be pictured as two-dimensional lines, two-dimensional circles numbered 1, 2, 3, and 4. So the energy levels are specific distances outward from the nucleus. The further away you get, the higher energy. So the lower energy is closest to the nucleus, and further out is higher energy. Energy levels can be compared to bookshelves. Electrons are located in these energy levels, just like you can have books on bookshelves. And each energy level can fit a maximum or certain number of electrons. An energy level that can have no electrons on it, 0 electrons. It can have less than the maximum number of electrons, but it cannot have more than a maximum number of electrons. For instance, energy level 1, that's the energy level, that's the circle closest to the nucleus. That can fit a maximum number of 2 electrons. It can also fit less than 2. You can put 1 electron in this first energy level or 0 electrons on the first energy level. And so you have these energy levels 2, 3, and 4 that also have a maximum number of electrons. The electrons on lower energy levels, like energy level 1, those are lower energy electrons. The electrons on higher energy levels, like energy level 4, those are higher energy electrons. And that's because it requires energy to move electrons from a low level up to a higher level. You can picture that again like the bookshelf. If you have a book on a low bookshelf, it takes energy to move it up to a higher shelf. This highest energy level, The one that's shown here is energy level 4. This is also the outermost energy level. It's the circle on the outside, and the other levels, 1, 2, and 3, are inside. And so that highest energy level is called the valence shell. And that turns out to be the most important energy level out of all the energy levels. And the electrons in that energy level are also the most important electrons out of all of the electrons in the entire atom. Why is that? Those are the only ones that really have access to other atoms. These electrons in this highest energy level, in the valence shell, are the ones that will react with other atoms. When valence electrons are lost, or there are electrons gained into the valence shell, that represents the formation of an ion and leading to an ionic compound. So when valence electrons are shared, that represents a covalent bond formation. The valence electrons are the most important electrons out of all the electrons. Or what's important is not just the valence electrons, but how many valence electrons there are. How many electrons are in that outermost energy level. So the number of valence electrons is also equal to the family number on the periodic table. So that's true for all of the elements that are the A series elements. Those are the 2 columns on the left and the 6 columns on the right, numbered 1 through 8A. Family 1A or group 1A, that number 1 indicates that there is 1 valence electron. What all of the elements in this family have in common, they're all different elements, remember, they all have 1 valence electron. And because of that 1 valence electron, all of the elements in family 1A have similar chemical and physical properties. Or if you look at family 3A, so this is meaning the number 3, is that all of the elements in this family, all of the elements in this column have 3 valence electrons. And because of those 3 valence electrons, all of these elements have similar chemical and physical properties. Just like human families have one thing linking all of the humans in the family together, their DNA, and lead to, as a result, similar properties. The same is true about chemical families. What links them together is the number of valence electrons, which results in similar chemical and physical properties. Family 1A, these are elements in family 1A, lithium, sodium, potassium, and rubidium. This family has the name Alkali Metals, and they all have in common 1 valence electron. What else they have in common is that they are all metals, because they're to the left of the stair-step line, and because of the 1 valence electron, they are all very reactive. So you can see the examples of actual lithium, sodium, potassium, and rubidium. What they all have in common is that they all have special storage, because they're so reactive that they'll react with air or water. All of the elements in family 1A, the alkali metals, are very reactive and will react immediately with water. Something like this happens when you take a piece of sodium and you put it in water. It's an immediate reaction which generates heat and light. And so there's a physical similarity of everything in the family. In this case, they're all metals. They're shiny, they're malleable, they're ductile. And then there's the chemical similarity of all of the elements in this family, that they're all very reactive because they all have 1 valence electron. And so you can determine the number of valence electrons, which is the most important, by looking at the family number for the A series elements.